it's Dr. Who's. Maximum and minimum values. So to the right is the graph of y equals f of x. Take my word for it, it's not even labeled. Absolute maximum and minimum values, or the extremes. The function f has an absolute maximum at x equals 10. Okay? So when x is 10, we have an absolute maximum value, and that absolute maximum value is 8. The function has an absolute minimum at x equals 2, and that absolute minimum value is not, or 0. In general, a function has an absolute maximum at c if f of c, or f of x for all x in the domain. So the absolute maximum, what would f of c have to be? Greater than or equal to. For all x in the domain, because at one of them you have to get that max. The number f of c, so the value, right, is called the absolute maximum value of f. A function f has an absolute minimum at c if
c is less than or equal to
f of c is less than or equal to f of x for all x in the domain of f. The number f of c is called the absolute minimum value of f. The extreme values of f are the absolute maximum and absolute minimum values of f. Okay? Local or relative maximum and minimum values. So the function f has a local maximum at x equals 4 and x equals 10. The local maximum values of f respectively are 5 and 8. The function f has a local or relative minimum at x equals 7. And the local minimum of value is, the local minimum of value of f is 12.
Would the value at x equals 2 not also be a local minimum?
Absolutely not. And here's the reason, right? So we need a definition, right, for a local. A function f has a local or relative maximum at c if, okay, so it's got to be f of c. So f of c, we're going to compare that to, so we got an x here, then we're going to compare that to f of x, right? And what are we going to say about it? If it's a local maximum, then it's going to be greater than or equal to f of x. When x is close to c on both sides. So that is absolutely why that is not, right? So 2, when x is 2, that's an absolute minimum. But it's not local because there's nothing to its left. Right? So it has to be on both sides, right? So you're looking for a little dip in the, yeah, okay, so around this point, right? And so we're looking close, right? So we're saying around this point, but close to it, this is the smallest value, so it's local. The number f of c is called the local or relative maximum value of f. A function has a local or relative minimum if f of c less than or equal to when x is close to c on both sides of c, right? The number f of c is called the local or relative minimum value of f. Okay, so a local or relative, and when you're looking for local, you're going to see a dip, right? I mean, you're going to see that around that point there are values greater than it at nearby or locally. Example 1a, complete the following for y equals g of x shown below. Okay, why don't you can do that, right? Do this. I shall pause this. So here we go, all nicely color-coded. Is it correct? Okay, good. So yeah, agreed. So we have an absolute minimum and also a local minimum, right? At x equals -3. So it's absolute. Since this is a likely, what, 4th degree or something? Likely a 4th degree. I mean, the simplest answer would be a 4th degree. It could be any even degree above that. It's an even degree. So it opens up, and it's got a positive leading coefficient. So it's an even degree positive leading coefficient. It opens up. So it has no absolute maximum, right? Because it just keeps going. But it does have an absolute minimum. Being of even degree, you're going to have either an absolute min or an absolute max, right? One or the other, not both. And we've got the values for it there, right? So we see we have an absolute minimum at -3. We also have a local minimum, right? Since it's coming from both sides. Okay. There we go. And you've seen this long enough if you're watching this, and it's all color-coded anyway, so. Do this. Whilst I pause. The absolute
the blank space for it. It's so much larger than any of the other blank spaces.
Maybe it was meant to line up with the previous one a little bit.
Yeah, I don't know. So, somebody was working on this late last night. So.
Can you bring it up to them? Tell them that I'm outraged. I'm outraged about
They've
the
taught you
test, too.
before, so they will not be surprised. Okay, numbers good? Right. So we have an absolute maximum. Now this thing, there's no arrows on this. It doesn't go anywhere beyond that. Right? So this is an absolute minimum, but not a local minimum. But this, I mean this, right, for those watching now, something will appear there. So this is an absolute maximum, right, because it's single-sided. This is or minimum. This is a local maximum and also the absolute maximum. This is a local minimum. This is a local maximum. This is nothing in particular. Right? It's like, it's an end. It's an end point, right? But that's it.
Is this the entire unit?
Yeah, because the outline I gave you just ends after today. And it's like there's a test on Monday, and then, oh, when we get back, sorry, there'll be a test.
Can this be the entire unit?
Yeah. Sure. You can take this as the entire unit, but you won't do well on a good chunk of the quiz. If we do not know what the graph of a function looks like, how can we find the local maximum and minimum values? Examine the graph of f below. So I mean, one way you could say is, well, we could just plug it into some software and graph it. Now, a problem with that is, depending on the scale of what you're looking, you may or may not see things, right? So we want some mathematical method which will help, and that's what we're going to develop here. Examine the graph of f below. For what value or values of x does f have a local maximum? Say it.
A, then C, then E.
A, C, E. You got that one aced.
Aha.
A, C, E. What is true of the derivative of the at these values of x?
It's 0.
Okay, it is 0, it is 0, it is does not exist. So either it is 0. So what's true of the derivative of these values? The derivative is 0. So either the derivative is 0 do you want the word or the number? 0 or
Write it, but make the O a 0.
the O is 0.
Like 0 or?
Is 0. Huh? Or the derivative does not exist. Does not exist. It's a little kinky. For what value or values of x does, well, you're going to introduce that, does f have a local minimum? B and D. Yeah. We didn't go that far. We should have extended the B and D. What is true of the derivative at these values of x? So yeah, the derivative is 0 or it is not. I'm gonna. The derivative is or does not exist. Right?
There's no point that it does not exist.
Yeah. Derivative doesn't exist.
Oh, son of a gun, I'm a failure.
Yesterday proves the no. No, that's not true.
I said layers, when you see how it works.
Well, yeah,
It's what inside, what's
consider
inside
it,
of
but
it.
Fermat's theorem, not his last theorem, the one that he sketched in a notebook and said,
And
the
lied
proof
about.
is left to the reader.
And
Which,
lied about probably because people went back later and they're like, there's no way he could have known about this.
well,
He was probably just wrong.
well, no, it was proven.
Yeah, but not the way that he could have conceived.
No, it was proven with a computer, I think, and like a lot of horsepower, computing power. But he did come up with the theorem. It was his last theorem, and very famous, and he sketched it off in the notebook. You're going to see this in textbooks, right? It's going to, and the proof is left as an exercise to the reader, right? Which means you just have to Google whatever that thing is and find somebody's proof of it, right? Say, really? Okay. Anyways, Fermat's theorem. If the function if the function f has a local maximum or a local minimum at c, then either f of c is equal to, sorry, f prime, so don't look from far away. Then either f prime of c is equal to 0, right? So the derivative at that point is 0, or it does not exist, right? As we've just seen from the diagram above. Note, the converse of Fermat's theorem is not necessarily true. So, for example, for f of x equals x cubed, f prime of x is 3x squared, and f prime of x is equal to 0 at x equals 0, but f of x does not have a local maximum or local minimum at x equals 0. Use your graphing calculator. You all know what the cubic looks like, right? So here's what your graphing calculator would show you. Okay, and this is called a point of inflection. Right. But this function, well, how would we describe f(x)? It's increasing on the interval negative infinity to infinity, right? So the function is always increasing. So just because you have a derivative that's 0 does not mean you have a local max or min. Okay? So you got to look at things. Okay. A critical number of a function is a number c in the domain of f such that either f prime of c equals 0 or f prime of c does not exist. Fermat's theorem says that if the function has a local max or min, then it occurs at a critical number, right? So what we're going to have to do is figure out the first derivative, figure out where it doesn't exist or where it's 0, and then go look there to see if we have a local max or min, right? No guarantees. Just says if there is one, it's going to be there. Just because, you know, these critical numbers exist doesn't mean that there is a local maximum. Okay, ready? Or not? A critical number of a function is, oh, okay, that's just repeating that, right? But you don't have that. It's at the bottom of your previous page, I'm guessing. Is it?
No.
Oh, wait. No, it's not. I'm looking at the same thing I just handed you. Determine the critical numbers of each function. Okay, so how do we get the critical numbers? Got to find the derivative. All right, what's the derivative of the? Okay, that's trivially trivial. Y prime x squared plus 12x plus 9. Okay.
Are you sure?
Yep. This is what I wrote before. If I do it twice, actually, the number of times I make the same exact mistake twice, and it can be a semester or 2 semesters apart. It's amazing. Anyways, okay, so we got y prime is 3x squared. Where does that not exist?
Where x
So where does y prime not exist? It doesn't not exist. So, all right, wait, that's too many negatives. So let's say this, y prime exists where? Everywhere. Is everywhere one word or two? It's got to be one word, I guess, right?
Yeah.
Everywhere. So y prime exists everywhere, right? Because what do we need? Critical numbers. What are the critical numbers? Where y prime is 0 or it does not exist. And it does not exist. I mean, it exists everywhere. So that's covered. And then we need what? Well, we got to figure out where y prime is equal to 0, right? So y prime is 0, y prime equals 0 when 3x squared plus 12x plus 9 is equal to 0, which means x squared plus 4x plus 3 is equal to 0. And we factor that. And we write down a bunch of stuff. And we say, okay, so the critical numbers are -3 and -1, right? So let's write this down. Critical numbers, you might want to squeeze your, oh no, you're fine here. You don't have to squeeze anything in here. Critical numbers, -3, comma, -1. Right, and I'm writing that in brace brackets to show it's a set of numbers. Right? So there's a set of numbers, these are critical. And it says, if there's a max, now okay, it's a cubic, so we know that there probably, it's not just plain old x cubed, which has just the point of inflection. This has got to have local max, local min, nothing absolute, right? Since it goes down to infinity and up to infinity. So. All right, y equals the absolute value of x. All right, so that means that y is equal to x if x is what? Greater than or equal to 0, right? So if it's positive, we just return the number. Okay, so if you're programming an absolute value function, it actually has to have an if statement in there, right? If x is greater than or equal to 0, return x. Otherwise, what do we return? Negative x. If x is less than 0. Okay, so we have two functions for y that we have to deal with, right? So then y prime, so what's the derivative of x? 1. So y prime is equal to 1 if x is greater than or equal to 0, and the derivative of negative x, -1 if x is less than 0. And does y prime not exist somewhere? Where? So y prime does not exist when x is equal to 0, right? So we have a problem. We have different derivatives at that point, right? So y prime does not exist when x is equal to 0. Otherwise, it's 1 or -1, so we don't have to worry about when is y prime equal to 0. Never. So what's the critical number? 0. Okay. That's the only value we have to worry about, right? And that's an absolute value function. It has a minimum at that point, right? We know that because we know what the function looks like. Y equals root x, or x to the 1/2. So what's y prime? 1/2 x, -1/2, right? Which we are then going to write as 1 over 2 root x. Right? Because we like to take, you know, if we can, we put it back into a radical form and we put stuff where it belongs. Because looking at this form, it's easy to say, what? It's easy to say that y prime does not exist when y prime does not exist when x and 0, what goes in there? Less than or equal to, right? If it's less than 0, we're trying to do the square root of negative. Can't do that. If it is 0, then we're going to try and divide by 0. Can't do that. So less than or equal to 0. Is there any point at which y prime is 0? Can you make 1 over 2 root x 0? No. No. Right? It's got to be a numerator. You got to get the numerator to 0, and it's 1. So, okay. What's the critical number? 0 is the critical number. All right. Now, this is when you might want to start writing the small, or getting out another sheet of paper and saying, see, this is continued on another sheet of paper. Okay. Oh, good. I'm going to have to write small too, because they didn't even stick them on different pages. Determine the local maximum and minimum values of y equals x cubed plus 6x squared plus 9x plus 2 and sketch the graph of y equals f of x, right? Now, did you do this in 30-1? No? Did you sketch graphs like that? Like just, did you find the zeros and multiplicities and?
Oh, yeah.
Yeah? Okay. I actually have, I have no idea what's, I mean, it's a bunch of stuff that used to be done in 20, I know, so that. Okay, so we could probably come up with some, based on what we know right now, or before we did this course, we could have come up with a decent-ish sketch of this thing, right? But now let's come up with a really decent sketch. All right, so where we're going to start with is we got to get y prime, which we've already done, right? It's on the previous, it's on the line above somewhere, right? It's just right up there. Okay, so it's 3x squared plus 12x plus 9. Well, we're going to realize that it exists everywhere, right? So, you know, we could say it's 3 times x plus 3 times x plus 1. Okay, so like, well, that's y prime. So, sorry, y prime is equal to that. And the critical numbers are -1 and, sorry, -3 and -1. All right. Now, here's what we're going to do. We're going to make a nice little table, right? Just like we did the other day. And we're going to look at each interval. Okay. And I'm going to do this not the way I did this last year, but the way that seems to make a little more sense now, but didn't last year for some reason. Okay, so let's squeeze a table in here. And we got critical numbers, right? So we've got -3 and -1, and in each of these intervals. So how many intervals do we have? Two numbers are going to split the number line into 3 intervals, right? So we've got below -3, between -3 and -1, and above -1, right? And we need to look at, yeah, 3. Okay. And of course, you know, do you really need, yeah, yes and no. You could actually just write 3 times x plus 3 as a factor, realizing that, you know, whatever. But let's put the 3 in. And let's put an x plus 3 in. And let's put an x plus 1 in. And then that's going to give us the sign of f prime of x, which is then going to tell us about f of x. Okay? And if you're filling this in, don't fill in the f of x just yet. Okay? Because I'm going to put a little twist on it. Actually, it's a bit of a rotation more than a twist. But. So 3 is always positive. X plus 3, if I add 3 to some number like -1,000, I think it'll be negative. If I add 3 to a number that's like -2, I think that'll be positive. That'll be positive. If I add 1 to that, negative. Okay, so I think I got all those filled in, right? So f prime of x here is positive, and here is negative, and here is positive. Now I'm just going to put a little rotation on the arrows, right? So we would draw an arrow and we'd say, so the first interval, if f prime of x is positive, then we know that f of x is increasing. So it's increasing, getting bigger. But we're going from left to right, so let's give ourselves a little clue while we're saying it's increasing. So we're going to do that by doing this. Because that's going to mimic the shape of the graph, right? So instead of just pointing us straight up, we're going to go up on an angle because we're drawing from left to right. So that tells me my graph's going to go up to the left. In this interval, it's doing what? It's going down, but it's also going to the right in this interval. So we're going to draw this. And then in this interval, it's going up to the right. Now you can see if we follow those arrows and go up, you're going to say, hey, you have a local maximum here, right, because you're going up, and now you're going down, and then you have a local minimum here, right? So we know that before we explicitly state that, right? And since it's a cubic, we know that it comes from -infinity and then goes off to positive infinity, right? So there's sort of the sketch of the graph. Now, at the same time, we're going to state this. Okay, so we want to say something, and the something we're going to say is the same as we did the other day, right? We'll just say, so f of x is increasing on the interval from -infinity to -3 and from -1 to infinity. All right, so all we're doing is just stating exactly what we stated the other day. Okay, and f of x is decreasing on the interval from -3 to -1. And then something is happening at -3, and something is happening at -1, which is not a surprise at this, not for this function, right? It's not a surprise, because we know this function. So we know we have a local maximum, and we know we have a local minimum, and we know they're locals because it's a cubic, and so the domain is all real numbers, right? Okay. So now what? Now we say, so step 1, figure out the thing and get the critical numbers. Well, I guess critical numbers would be like, well, that's part of step 1. Step 2 is, let's do the chart. Step 3 is, let's explicitly state what's in the chart. Step 4 is, yeah, well, we need to, so we got to determine the local maximum. So we know there's a maximum at -3. So we need to get f of -3, right? We have to now determine f at x. So step 4, determine f of x at the critical numbers. Okay, so we need f of -3, which is -3 quantity cubed. So make sure you're putting the -3 in brackets. Not that it matters when it's cubed, but it does matter. Plus 6 times, now really matters. So 6 times -3 quantity squared plus 9 times the quantity -3 plus 2. And that's -27 plus 54 minus 27 plus 2, which is 2. Because -27 minus 27 is -54 plus 54 is 0, 2. Boom. So we have so we could now say we have a local maximum at -3, 2. Right? How do we know it's a max? Look where it's pointing, right? We've gone up to get to -3. When we reached it, we are at -3, 2, and now we are heading down. So that's a local maximum. We know, based on this, that we have a local minimum at -1, right? So now we got to get f of -1, which is -1 quantity cubed plus 6 times -1 squared plus 9 times -1 plus 2. Okay? Be very explicit when you're working this stuff out. I know it's a bit of a pain, but based on the mistakes that some of you are making, it's a pain you need to feel, which you will feel when you look at it, because you go, oh my god, I squared in there, I didn't distribute a negative sign through brackets. That would happen a lot, right? Didn't distribute the negative sign through the brackets. So -1 plus 6 minus 9 plus 2 is -10 plus 8, or -2. So we could say we have a local minimum at -1, -2. Okay, and notice it says determine the local min and max values. So we've done that. Okay, so now we can draw a decent-ish sketch. So we got critical numbers, -3, -1. When x is 0, what's y? Right, because that's easy. It's 2, right? That's easy to figure out, right? So we've got this guy here at 2. Okay, we got a point here at -3, 2. And we've got a point here at -1, -2. So we know that this function is increasing from -infinity to here, right? So it's coming up to here, at which point the derivative is 0, right? So we flatten out, it's now horizontal, right? The derivative is 0, so we've got this horizontal. And then we're coming down until we reach here, and that's a minimum. Again, derivative is 0. Okay, and then we're coming up fairly steeply-ish, since that point is easy to determine, right? You're just throwing in a 0 for x and getting 2. Okay, and then this does this. Okay, and then we quickly pause. Okay, and then here's our graph, right? So we're coming from down here. Do I need this? Can you find someone? Take a tab or something. There, it's gone. Okay, we're coming down, so we got -3, 2, and then we're coming down to -1. So local max, local min, y-intercept, and away we go. Okay, cool. Get rid of that. Go back to this. Determine the absolute maximum and minimum values of the exact same thing on the interval from -5 to 0. So now what we're doing is we're putting a restriction on this function, right? And it's a real life thing, you put a restriction, it's like time is positive, so we're going from 0 to whatever, right? So we're putting a restriction on this, and we're saying, okay, if you graph from -5 to 0, so we already know what's going on. We have a local maximum, we got a local minimum, and they're within that interval. So what we now need to do is one more step, right? We need to look at the endpoints. We need to say what's happening at -5, what's happening at 0. So we need to look at the endpoints of the interval. We need to look. It's not really look, although if I regraphed it, we could, at the endpoints. Which means we need to evaluate f of -5. Okay, so pretend we just didn't, we haven't seen the graph. It's probably easier to pretend. Probably just don't remember.
So now we're on the left side of the interval.
Yeah, so we are doing, now, no, this includes -5, right? So we got that. So we would need to look at, okay, so we've looked in between -5 and 0. We know we have a local maximum at -3, 2. We know we have a local minimum at -1, 2. But we don't know about -5 and 0. So we need to evaluate these. So f of -5 is the quantity -5 cubed plus 6 times the quantity -5 squared plus 9 times -5 plus 2. So that's -125, and that's 25 times 6, so it's plus 150 minus 45 plus 2. So we got 152 to the positive and 167 to the negative, so that's -15. No, it's not actually right, is it? Got one -18. You're right. It's good. It's good. You got to check up on this. So we have a point at -5, -18, right? We got the point -5, -18. Okay. So now we got to do f of 0, which is 2. That was easy. So we got the point 0, 2. So now we put everything together, right? So we say, okay, I have the point -5, -18, and I have the point 0, 2. Okay, and this is all we're interested in, right? So we're not interested in, so now our function, there's no more arrows on there. Our function begins and ends. Function begin and ends on the red dots. So what is the absolute minimum value? -18, right? So the absolute minimum value is at an absolute minimum value of -18 when x equals -5, right? Okay, so the absolute minimum occurs at -5, -18, and the absolute maximum okay, well, we kind of have two, right? We've got -3, 2, and we've got 0, 2. Okay, so in that interval. Aha, the procedure. So find the values of f at the critical numbers of f prime. Okay, so you figure out f prime and you figure out the critical numbers. Then you evaluate the function at those critical numbers because you say Fermat's non-last theorem, or one of his other theorems, says that if there is a local max or min, then it will occur at one of the critical numbers. It doesn't say there will be one. It just says if there's one, then it's going to occur here. Find the values of f at the endpoint. So look at f of a and f of b, right, if we are restricted to an interval. The largest of the values from step 1 and 2 is the absolute maximum value. The smallest of these values is the absolute minimum value. Okay? Let's keep going. Procedure for finding the absolute maximum values of a continuous function on a closed interval from a to b. It's giving you that, right? Do they at least? Well, I have infinite space. Well, it's finite, but. So determine the local and absolute maximum and minimum values of y equals x to the 2/3 times 5 plus x on the interval from -5 to 1. So the first thing we got to do is get the derivative, y prime. Now, we can make life a smidge easier if we just distribute the x to the 2/3 into the brackets and just do the derivative of the sum, rather than treating this as a product and going through all the pain, you know. So I'm just going to do that. It's your choice, right? It doesn't matter. Okay? It's like that question on the, oh, I can't mention the question on the test. The head perked up. Wait, which question? Okay. There's one where you could have done it a couple of different ways, and one was potentially easier than the other, and it didn't make any huge difference.
You could do one of the questions more than one way.
You could do many of the questions more than one way, but.
Like the calculator.
Yeah, you could have done, except. Yeah, we just don't have that problem, right? The reason is just in case you go to U of C that doesn't allow calculus. So you might go somewhere where they say, now you're going to go buy Mathematica because you have to learn. I tried it, man. I bought it for a year, but it's just. Anyways, so I'm just going to multiply x to the 2/3 and get 5x to the 2/3 plus x to the 5/3. Okay? Doesn't matter. If you're using the product rule, you're going to get the same derivative, right? Which is, so y prime is equal to 10/3 x to the -1/3 plus 5/3 x to the 2/3. Now, we have to factor this, right? This is why you think we always ask, we have the parameters in factored form, or derivatives in factored form, right? The reason is, because we got to find zeros, we got to find critical values, we got to figure out domains. Hey, it doesn't exist here, blah, blah, blah. So how do we do this? Well, we factor out the smallest of 5/3 and 10/3, which is 5/3, and we take the smallest power, which is x to the -1/3. So that'll be my common denominator. So to get 10/3, I'm going to need a 2. And I already got that there. Okay, and then plus, and so I've got a 1, and I need a positive 2/3. So I think that's just going to be 2 plus x. Right? I'm going to look at my thing there. Yeah, and it is. Woohoo. Okay, and now we're just going to write that in a nicer form, which is to say it's 5 times 2 plus x over 3 cube root x. Right? So the x to the -1/3 goes to the bottom where it becomes x to the +1/3, which is the cube root of x. Okay? Cool. So we've got 5/3, like who really cares? 5/3 is just 5/3, but we've got a 2 plus x, we've got a factor of 2 plus x, we've got a factor of cube root of x. So when does this not exist? So y prime does not exist when x is equal to 0, right? Because cube root of 0 is 0, and then you're trying to divide by 0, and I bring up the NHL saying, you can't do that. No, it's cube root. You can do cube roots of negatives. Okay, and when is y prime equal to 0? When x is -2. Okay, so basically we're just looking in the numerator for when, how do I make the numerator 0? That's going to make the expression 0. So we have two critical numbers, right? So let's write that down. Critical numbers are -2 and 0. Okay, now you might think this is overkill. Yeah, they're obviously that, but I think if if you explicitly state them, you're not going to sort of lose one at some point or something. I don't know. It's always possible you could lose a critical number. Okay, so let's make a chart. All right, so we've got our factors. So let's just call the first factor, let's call that 5 times 2 plus x, right? Because whatever the sign of 2 plus x is, the 5 is just going to. And let's call the bottom one 3 cube root x. Okay, and we have -2, and we've got 0. Okay, we don't need to extend that far. And we're going to get f prime of x from this, and then we're going to get the direction of f of x from this, be it increasing or decreasing. All right, so if x is like -1,000, then 2 plus -1,000 is probably negative. And if x is -1, yeah, that'll be plus. Cube root of a negative is negative, and the cube root of a positive is positive. Okay, so we fill this in, right? Get it right. If you don't get it right, it's like, things go really bad. So f prime of x is positive, and then it's negative, and then it's positive. So f of x on the first interval is going like up to the right, right? And then it's going like down, and then it's going like back up again, right? Now we know this is not a cubic. There's a cube root in there, right? So, I wouldn't just sort of sketch out, but that's the idea, right? It's increasing until we hit -2. There's going to be a local maximum or perhaps absolute maximum at -2. Don't know for sure, right? Because we still have to do endpoints of the interval, right? So we have to work out, well, okay, let's say, I'm just going to write it, right? F of x is increasing from negative, oh wait, do we really need to? Well, we're on the interval -5 to 1, right? So let's do this. So -5 to -2, right? And from 0 to 1. And f of x is decreasing from -2 to 0. Okay, so what we're interested in is we need to know f of x. So we need, where am I going to do this? Where? I'm going to go up here. So we need f of x when x is -5, -2, 0, and 1. Okay? So the -2 and the 0 are the critical numbers, right? Where we know we have at the least a local max at -2 and a local min, and they could be absolute as well. And then we also need -5 and 1. Okay, so just going to work them out, right? F of -5 is -5 to the 2/3 times 5 plus -5, which is 0. Whew, dodged a bullet on that one. Right? That's the cube root of -5. Who cares? Got a 0 there. So we have a point -5, 0. F of -2 is -2 to the 2/3 times x plus, 5 plus -2, which is 3 times -2 to the 2/3. Come up with anything fancier for that? Okay, so it's 3 times, sorry, it's going to take a little while. So it's 3 times the cube root of -2 quantity squared, which will be 3 times the cube root of 4. Okay, so we can do a little bit of simplification in here, right? Because we can do we can't do the cube root of -2 squared, but we can write it as the cube root of 4. And that gives us an idea as to its size, right? I mean, the cube root of 4 can't be 2, because the cube root of 8 is 2, so, and it's not like 1.5, but it's like over 1. Okay, so we've got the point -2, 3, cube root 4, which we know cube root of 4 is like over 1, and then 3 times that, it's like some number bigger than 3, less than 6. Got an idea. F of 0 is 0 to the 2/3 times 5 plus 0, which is
0.
0, right? 0 to the 2/3 is 0, and then the rest of it's like whatever. So we've got 0, 0. And f of 1 is 1 to the 2/3 times 5 plus 1, which is 6. Okay, now, I think we've... All right, so we have 4 points. Right, we have 4 points in which we are interested. Is that grammatically? We have 4 points we are interested in.
Which we're interested.
In which we are interested, I think it's that. All right. So we got the point negative. So, all right, any of them obviously low? The zeros, right? Okay. I don't know what the 3 times the cube root of 4 is, but I do know that it's greater than 0. And I'm kind of sure that it's less than 6, right? It has to be, because the cube root of 4 can't be 2, right? Cube root of 8 is 2. All right. So, where are our locals? Now, the negative 5, 0, is that a local? Absolutely not, right? Because it's one side, it's just there, right? To be local, you need points on either side of negative 5, but we're just at negative 5. So we have an absolute. All right, where are we going to say this? So we have an absolute minimum at negative 5, 0. What about a local minimum? Oh wait, is there another absolute minimum? Sorry, 0, 0, right? So absolute minimum at negative 5, 0 and 0, 0. How about a local minimum? Yeah, so at the point 0, 0, right? So local minimum at 0, 0. All right, do we have a, okay, what's f of 1? Okay, so 1, 6, what is that? Absolute maximum, right? Is it also a local? Absolutely not. Because it's on a boundary, right? So absolute max at 1, 6. Is there a local max?
Yeah.
Where?
Negative 2 and 3.
Negative 2 and 3 cube root 4. Okay, so we know that, right? Just looking over this little diagram here, it says, well, you're going up to that point, and then you're coming down from that point, so that's going to be a local. I don't know what the cube root of 4 is, but I do know it's not 2. It's less than 2, right? So you don't have a calculator, but you got to kind of know the cube root of 4 is less than 2, and 3 times that will be less than 6. So, okay, so can we sketch out what we've got here? What do we got? So we got a 0, 0. We've got a negative 5, 0. We've got a 1, 6. 1, 6. Yeah, we can save a couple for tomorrow. There's no rush. We got a 1, 6, and we've got a local max at negative 2. So negative 2. All right, so absolute minimum rising to, let's put this about here. Right, because we got to come up. So starting here, we're coming up to here, and then we're going down to 0, 0, and then we're coming back up again. So, I don't know. Okay, but it's not a cubic. So let's go look for reals. Oh, right, because it didn't exist at 0, right?
Holy wow.
All right, wait a second. It didn't exist at 0. It does not exist when x is 0, right? So what does that mean? Well, it means that we've got, it's going to v. We've got a kink. There we go. Ha! See, more information than we knew. All right, and so we were looking here, right? Negative 5, we had a 0, 0, we had a 1. You take my, so we had this, and this, and this. Oh, and this. right? So at -2, we had the local maximum. At -5, we had the absolute minimum, but not local because there is nothing, right? I should redo this to go from -5 to 1, but I'm not going to. And there we are. Okay. And that didn't exist, so yeah, we should have suspected something along those lines.
So would we have to know to do like the weird V-shaped thing?
You kind of should know just based on the fact that hey, it didn't exist there, right? So what happens if it's 0? Then we know you're flattening out. You're becoming 0. If it doesn't exist, then you got a kink. So
Okay.
yeah, we should know that.
Okay.
Okay, so stop now. Do these next 2 tomorrow, or continue?
Yes. Stop now.
Stop now. Do this one and then stop.
Actually, this is pretty easy.
All right,
Actually,
let's do
I
this
know
one,
I've
and
already started
then
it. I would
yeah,
like to know
and then
how
we'll do the next one tomorrow, right? Because we're gonna run out of time anyways, probably. Okay, so determine the. So this just asks for local maximum. So if we think about this function, right? Let's say if this exists, well, it exists. Okay, so we got x to the 4th. So when x gets to be a really large negative number, x to the 4th is going to be a really, really large positive number. But when x is a really large negative number, e to the x is going to be 1 over e to a really large, okay, so, and e to the x can't be 0 or negative, right? So we're going to have a positive times a smaller number, so I think it's going to kind of tend to 0, right? It's not going to get real big. And as we go positive, it should take off like a bat out of hell, right? X to the 4th is going to get really large, e to the x is just going to be, like 3 to the x, whatever, big. So it's going to take off. Okay. So we want a local max and min value. So what do? Well, we find the derivative. And this is a product, so we do x to the 4th times e to the x. Okay, that's f times g prime, right? First function times the derivative of the second, plus the second function, e to the x, times the derivative of the first, which is 4x cubed. Okay, and we do a little bit of factoring, so we've got an e to the x, but we've got an x cubed, e to the x, and then this will be x plus 4. Okay. And we need that, right? We have to have this, because we need to know where does it not exist, and it doesn't not exist, right? Or it exists everywhere. Must stop saying doesn't not exist. Okay, so y prime exists everywhere. Or you could say it doesn't not exist. Don't say that. And y prime is equal to 0 when? Equals 0 when x equals 0 and x is equal to -4. Okay. So our critical numbers are -4 and 0. Right? So I'm going to write that down just because I always write that down. So we've got a set of 2 numbers. The critical numbers are -4 and 0. Okay, so let's squeeze the chart in here. Okay, so we got -4, and we got 0. And the factors we have are x cubed, e to the x, and x plus 4, right? X plus 4. Taking these and using a sign analysis, we will get the sign of the derivative, which will then translate into the direction of, or the intervals of increase or decrease, right? All right, so x cubed. Well, if you're negative, you're negative. E to the x, always positive, right? Are you sure? Say, I'm positive. How often do you get to work that in? X plus 4, so if you're -100, that's probably negative. And if you're -2, that's positive. And we're going to see a lot where it increases, then it decreases, then it increases, right? And don't get in the idea that, oh, it's always going to, if it increases here, then it decreases. They could both increase. We're looking at what? And we're looking at this, right? It's swooping up on either side, right? Well, no, sorry, that would be increasing and then decreasing. And then we don't know. But we would be looking at this, and then it would be increasing and increasing. Yeah, so you could have increasing with one branch going up and the other one coming from down below, right? Okay, and then you have to figure out, okay, what's happening at this point then. All right, so f prime of x is positive, then negative, then positive. So we're increasing, decreasing, increasing. So that again, remember it's not a cubic. This is like nowhere near a cubic. So, you're not necessarily drawing a very smooth little cubic-y thing. Okay, what else can we say? So we could say f of x is increasing from negative infinity to negative 4. And where else? From 0 to infinity. F of x is decreasing from negative 4 to 0. Okay, and we weren't directed to a specific interval, so we really only need to look at f of x at two values, right, which are 0 and negative 4. Sorry, negative 4 and 0. Okay, so let's swoosh back up here. So we need f of negative 4 and f of 0, right? So we need f of x at the critical numbers. Okay, so f of negative 4 is negative 4 quantity to the fourth, because that's going to come out as positive, right? And then e to the negative 4, okay, which is 256 e to the negative 4. All right, so if we say that e is 3, which it isn't, it's 2.7, but we say it's 3. Then we got 3 to the negative 4, which is 1 over 3 to the fourth, which is like 81, right? So we got like 256 divided by 81. Let's make life easy. Let's call it 256 divided by 64. It's around 4, right? It's like 4-ish. Okay. So yeah, you don't need to know that, but yeah, you could say it's like 4-ish. It's somewhere in that ballpark. Okay, so we've got the point negative 4, 256 e to the negative 4. And we want f of 0, which is 0. Requires no further calculation. 0 to the fourth times, who cares? Times 1, actually. But that's still 0. Okay, so we got the point 0, 0. Okay, now, according to our chart then, we should have a local max at negative 4 and 256 e to the negative 4th. And it just said local, right? So there's no absolute. So local max. Okay, and the chart's telling you where, right? Going up, going down, that means that you had to peak. So at negative 4 and 256, 4-ish. And then we're going down, and then we're heading back up. So then there's a local min at 0, 0. There should be no kinks, right? Because there was nowhere it didn't exist. Wait, that's again. It exists everywhere, right?
Also, because the ISPs in the UK block them.
Yeah, that's yeah, and then you watching the news last night? Yeah. Britain has its problems. Okay.
I know you know that too when people are at home.
Okay, so we got a 0, 0. We got something that's what does it look like? So we think it's coming from somewhere down low and then peaking here and then dropping down and minimizing there, and then and that's kind of rounded.
It's so pretty.
Yeah, and then that's kind of rounded, and then we can go look at it, and that's Yeah, and that's four-ish. Okay, it's four and 3/4-ish. Okay.
So far from 4.
Look, four-ish means in the vicinity of 3 to 7.
So can I just write any answer I want and say that it was the actual answer-ish?
If you're graphing it and you're graphing it up at 256, I would say there's a problem there because we know it's not 256, seeing as you're dividing it by something. Yeah, I don't expect you to, I mentioned the shape, right? You're really interested in the shape. What's this thing look like? Well, it goes there and then it comes up and has a local maximum, it has a local minimum, and then it takes off, right? It actually really flattens out here because an x to the 4th really flattens out around 0, right? Like x squared just kind of touch and go. X to the 4th, it's, because you get these values being really, really small and then the e to the negative whatevers. Okay, so we'll stop there. I will save this notebook file and I'll PDF it and put it up, and then I'll replace it after tomorrow, right? But so just remind me, reopen the notebook file and save it, and then we'll finish and do the last one. Unless you want to do it tonight, and then we can just kind of look at it. Maybe that's an idea, huh? Okay, and then tomorrow we'll finish that. The rest of the period's work period. All of the break is a work period. Whoa. Well, do what you want. And thought we'd start with a small recap. So, what is it that we want to know about the first derivative when we're doing this curve sketching stuff? Or max and min. We want to know when the first derivative is 0 or does not exist. And what else is really important that we know about the first derivative? Plus and minus, right? The sign, right? We need to know if it's positive, which says that the function we're graphing is increasing, or if it's negative, we're decreasing, right? So that's information we can't lose. So we know that we may have a max or min, but we also know with x cubed we'll get a derivative of 0, but we will not have a maximum or minimum, right? Okay, so let's just move on to the end. Here we go, the end. All right, so step 1 is to do what? Do the derivative, right? So y equals 2 cos x plus sine 2x. So let's come up with y prime, right? Should be a relatively easy one. So what do you got? Negative 2 sine x cos. No, let's just throw the 2 in front. Right? So negative 2 sine x, right? So we got the 2, and then the derivative of cos is minus sine. And then derivative of sine 2x is cos 2x times 2, or we could just write that as 2 cos 2x. Now, all right, so what do we want to do? Well, we want to find out when this is 0, right? So, or where it doesn't exist. So that's kind of handy if we can get a factored form, right? So we could take out like a negative 2, I suppose, right? Negative 2, and then what do we get? Sine x minus cos 2x. Okay, so does that help? A little bit. But we got a formula for cos 2x, right? What's the cos of 2x? I mean, there's a lot of cos 2x. I actually know where the formula sheets are now, because I stumbled on them the other day. All right, so cos 2x is equal to cos squared minus sine squared. All right, well, yeah, but that'll still leave us with a sine and a cos. It's equal to 2 cos squared x minus 1, but we'll still have a sine in there. Or it's equal to 1 minus 2 sine squared. That sounds promising, right? Because then we'll have a sine squared, and we'll have a sine, and we'll have 1, and maybe that'll factor. All right, so let's go with that. So we will replace the cos 2x with a 1 minus sine squared x, right? Okay, so what do we got? So sine x minus 1 minus sine squared x. Okay, so what does that give us? So we're going to get a sine squared x, or minus sine squared x.
No, it's positive.
Positive, right. It's going to be a positive sine squared. All right, so let's go through and just negative 2. Okay, so what do we got? Sine squared x plus sine x minus 1. Yeah.
It's supposed to be 2 sine squared x, so you can end up with like 2 sine x minus 1.
Oh, 1 minus 2 sine squared x. Yeah, good. Knew there was something in there. 2 sine squared x plus sine x minus 1. Okay, so does that factor? What do we got? Like 2x squared plus x minus 1. So 2 sine x and a sine x plus 1 minus 1. Does that work? Yeah, I think so, right? 2 sine squared plus 2 minus 1 is plus 1 minus, yeah. Okay, so good. Anytime you factor something, FOIL it out. I can't remember if you guys are the 20s, but somebody was, there's some wrong factorizations, and then things just don't work from that point on, right? Because you don't get the correct solution. Okay, so where does that not exist? No, it doesn't not exist, right?
Where it exists.
Yeah, it exists everywhere, right? So, when don't things exist? Well, when there's zeros in denominators or negatives under radical signs, none of which we have here, right? The sine function is continuous. So y prime exists everywhere. So, when is y prime equal to 0? So 2 sine x minus 1 equals 0, right? So 2 sine x is equal to 1, and sine x equals 1/2. And I think we're on a limited domain here. We're just going 0 to 2 pi. So when is sine 1/2? Right, pi by 6, pi by 6, yeah. All right, and what else do we have? Well, sine x plus 1 equals 0. So we've got, let's do this here. Sine x plus 1 is 0. Sine x is negative 1. So x is negative 1. Let's right there. 3 pi over 2. See me sketching out sines and cosines in the air. Yeah. Okay, so well, what do we do then? We're going to make our little table, right? We're only going from 0 to 2 pi. So we're going to have 0 and pi over 6 and 5 pi over 6 and 3 pi over 2 and 2 pi. And we just got to figure, okay, so what's happening in those intervals, right? And what are we interested in? We're interested in the sign of the derivative, right? Which is here. Okay, so that negative 2 is part of it, right? Like we got to take that as a factor. Like negative 2 is a factor. Like when you're solving for this being 0, if I set that equal to 0, I just dump the negative 2, right? But if you do that and then you carry that into your chart, it's all going to be wrong, right? Everything will be pointing the wrong direction. You'll be saying it should be going up, it should be going down. Okay. So we have to remember that we need the factored form of the derivative, this guy here, when we're going to do our chart. Okay. So we need that -2. And we need the 2 sine x minus 1, and we need the sine x plus 1. And we have room here. Let's say we do. Okay, so we got 0, pi by 6, 5 pi by 6, 3 pi by 2, 2 pi, got a factor of -2, which is kind of easy to fill in right off the bat, right? It's just all negative. We have a factor of 2 sine x minus 1. We have a factor of sine x plus 1. Those are our 3 factors, so once we've figured out what sign they are in each of the intervals, we will get the sign of f prime of x. Which will then tell us what's happening in that interval for f of x. I'm going to extend the page just a bit. All right, so all we're going to do is fill in that table. So you want to give it a shot? Fill the table in. Okay, so we figure out in each interval the sign of 2 sine x minus 1 and sine x plus 1, which will give us then, so we've got 2 negatives and a positive, so this will be positive, negative, positive, and positive. Well, that's a little interesting, right? Because we haven't run into that before. Before we look, it's up and then it's down, and then it's up and it's down. So so this is going up. And this interval is going down. So this implies there is a maximum, right? There's going to be a local maximum here. And then, or absolute, we don't know. This goes up. So there's minimum, right? Just you kind of imagine the shape of it, right, if I'm drawing that. And then this goes up. So what's happening at 3 pi over 2? But it's not, it exists everywhere, right? Inflection. So there's a point of inflection, right? So just think of y equals x cubed, right? It's coming up, 0 derivative, still going up, but it increases on that interval. This increase. Now, if there was a discontinuity, right? So if it didn't exist, then we'd know, okay, there's something going on, right? It could be a point discontinuity. Right. So then I'm just going to put in the, the f of x is increasing. From 0 to pi over 6, and from 5 pi over 6, all the way through to 2 pi. Okay. Now, if it didn't exist at 3 pi over 2, then I'd have to break that up, right, and say from 5 pi over 6 to 3 pi over 2, and then from 3 pi over 2 to 2 pi. And it's decreasing in the interval here, pi over 6. So f of x is decreasing from pi over 6 to 5 pi over 6. Okay, so that's sort of belt and suspenders, right? I mean, it's just taking information that we have in the table and just writing it down, right? So that when we draw this, we can look back to the table, we can look back to the words and say, hey, is everything matching up here? Did I read this correctly? Okay. All right, so what do we got? And then what do we have to, so we got to work out some values, right? So we need values at 0, pi over 6, 5 pi over 6, 3 pi over 2, and 2 pi. Okay, so we need those values because we got to figure out local max and min values. All right, so we need y for x is equal to 0, pi over 6, what's the next one? 5 pi over 6, 3 pi over 2, and 2 pi.
Don't you only need it for the middle three because it's local values, so the ones on the ends of the integral don't count?
That's true. Absolutely.
Also, don't we not need it for 3 pi over 2 because it can't be a local angle?
That's true too. But we're starting to work. But you know, if we want to do a reasonable sketch, you know, we'll get some values. So these, we'll know, well, it starts up here and then it does that. But yeah, you're right. Okay. And it didn't say absolute. Maybe it should have. So if it said absolute, we would have to for sure work out 0 and 2 pi, right? Because we need the boundaries. But we could do them anyways, right? It's just here. So, all right. Let's say f of 0, that's not really f, right? So 2 cos 0 plus sine of 2 times 0. Really looks like a 20. Sine of, all right, so that's 2. So we got the point 0, 2. Pi by 6. 2 cos pi by 6 plus the sine of, so 2 pi over 6 is pi over 3, right? So I'm just going to throw in a pi over 3 there. That's 2 times x. Cos pi over 6, what's that? Root 3 over, yeah, root 3 over 2. So that's just going to be root 3. So we got root 3. And the sine of pi over 3 is root 3 over 2. So we got a point at pi over 6, and that'll be 3 root 3s over 2. Right, because the first root 3 is 2 root 3 over 2 plus root 3 over 2. It's 3 root 3s over 2. And what's next? 5 pi over 6. 2 cos 5 pi over 6 plus the sine of 5 pi over 3. Okay, and all I'm doing is multiplying the 5 pi over 6 by 2 when I stick it in there. 5 pi over 6, same as pi over 6, but it's negative, right? So that's going to be the negative of root 3. And 5 pi over 3s is, what, quadrant 4? Pi over 3, so it's a minus root 3 over 2. So 5 pi over 6 and negative 3 root 3 over 2. And 3 pi over 2. Two cos 3 pi over 2 plus the sine of 3 pi. Cos pi over 2. So that's 0. Sine of 3 pi is that 0. And 2 pi. 2 cos 2 pi plus the sine of 4 pi. So what's that, 2? 2, yeah, 2 plus 0, 2. So 2 pi and 2. All right, so now we should be able to come up with a fairly decent sketch, right? So what we're doing basically is putting this together, right? So put this, so from 0 to pi over 6, we're going to increase. So we've got some points that we can plot. Right, we're starting at 0, so we got 0, let's do a pi over 6, 2 pi over 6, 3 pi over 6, 4, 5 pi over 6, 6, 7, 8, 9, 3 pi over 2, 10, 11, 12, 2 pi. And how high do we go? 3 root 3 over 2. Root 3 is like what, 1.7-ish? 1.8? That's about 2.7, a little less than 3. So we knew we need some 2's, and we need some little less than 3's, and we need a little negative less than 3 down here. So this will be 3 root 3 over 2, negative 3 root 3 over 2. All right, and we got some points, right? 0, 2, pi by 6, and 3 root 3 over 2. 5 pi by 6, and the negative of that. 0, 0, and 2 pi 2. Okay, so we should be increasing to go from, which is good, because we got to go from here to here, so we're going to be increasing. And then we're decreasing down to here. Okay, so let's, then we're going to, we got a point of inflection there, and we end there. Okay. Let's bring up the real thing. There's the real thing. So 0, 2. Whatever this maximum point is, which is about 2.6-ish. So there's our 3 root 3 over 2. There's our negative. Let's move the whole thing a bit. 3 pi over 2, point of inflection. Minimum at 5 pi over 6. Maximum at pi over 6, and off the chart. Maximum at pi over 6. Nice, huh? Okay, that's it. Questions? No, nothing you want recorded for posterity?